Okay, everyone, thank you for making it to the second hour. This is our last second hour. Now, that should be like, yay, but recall that that means next week, double lecture Friday. Why do we have double lecture Friday? Because next week's the exam. And the week after that is the final exam review. And after that, I heard that a meteor is going to hit the Earth, so none of this matters. Whatever. Anyway, here's the thing. This is a little awkward. Normally, I've got a room full of people asking some questions at this point, and there's actually some like giant squirrels in here. That's a whole other story. But they're not really asking any questions. I see them dancing around sometimes. But I'm also hesitant to just cancel class. I thought about it. But here's the thing. You're paying me, right? If I start canceling class willy-nilly and you're paying me, that's pretty screwed up. So tell you what, this is the last extra hour. I don't have a heck of a lot to say, so we're gonna make it short. But let me tell you a couple things. The thing I'm gonna talk about, this is where it gets kind of awkward. This coming Wednesday, there's a part of it that I didn't explain in much detail. So I thought I would actually do that now. So it's kind of weird because I'm talking about now something you'll see on Wednesday. Now I'll go ahead and explain it all. You don't need to like hit pause and wait till Wednesday. Why don't you just watch this? It'll be quick. And then when you see the material that I'm discussing now on Wednesday, you'll be like, oh yeah, that's easy. That's probably of maximal benefit. I'm also going to do a little reviewing of stuff that I think will make it to the third exam. And remember, the final is comprehensive. And the last bit here, of course, as usual, is just to give you a little something more. Now, I'm going to talk about matrix mathematics and how it applies to quantum mechanics. Now, I know you're all saying, well, I'm never going to use that. You're probably right. But here's what you are going to use: your head. And the more that gets sharpened, the better off you are. Let me also point this out to you. You're all about to go out into the world. I've said this to you before. No one is going to give you a break for being 21 or 22. No one's going to give you a break at all. They're going to use it against you. Oh, you're going to med school. Okay. Do you want them to be better prepared than your colleagues? Do you want to be the last person in class? How do you not let that? I know it feels like that's the way all the time, right? People are always putting you down. You're always the last one. Now here's the thing. All right, that could be true. That would suck. But if we don't prepare as well as we can, I guarantee you, then it will be true every time. It still might be true, I hope not. But I know if you don't try, that people will put you down, that you'll be the last in the class, then it's guaranteed, right? If we try, there's a chance. It may not be a good one, all right? But there's a chance. So, again, today I'm going to tell you a little bit about matrix mathematics and how it applies in quantum mechanics. I'm going to do some reviewing, so it will be of use to your exam, but mostly it just makes connections up here where there weren't ones before. It can come back to you in ways that you don't necessarily perceive, but I guarantee you they're there. Because people who have classes like this and do well will do better in other things. They are correlated. We know that they're correlated. Remember, I told you that when grad students come in, we look at their math score. Oh, what if they're an organic chemist? What if they're a biochemist? They don't use any math. A little bit. That's true. It doesn't matter. Their math score is still the #1 predictor of their success. Now, you may say, oh, BS, or I don't like that. Well, you don't have to like it. It still is, and we still use it. So, there you go. All right, so anyway, I'm back. Okay, matrices in quantum mechanics. It turns out that quantum was originally expressed in matrix form. Okay, now let's take the eigenvalue equation, which a lot of you choked on the second test. Operator, it has a hat. Function, eigenfunction, the eigenvalue, and then the eigenfunction is still there, right? That's why this stuff is kind of difficult, because, if it was just some function in a number, that, anything could do that. That's not hard. but we've got to have an operator function, and the function still has to come back exactly as it was before. Anyway, you've had this stuff. Okay, now it turns out that I can do the exact same thing with matrices. Let me just throw up some numbers. I'm just going to write some examples. Okay, here's an operator, and it's in a matrix form. And anyway, I'm just writing some stuff down. You know what a matrix is. Okay, so let's call that the operator. Let's call this the eigenfunction. Does it work? Well, I bet you've forgotten this. I have to look it up. I have to look it up because I forget. Minus 2 times 1 plus 0 times 0. Okay, next one. 0 times 1, 2 times, plus 2 times 0. And that's minus 2, 0. And here's another little fact of matrices. You can factor numbers out. Okay. Operator, 1, 0. Number, 1, 0. So this is the eigenvalue. Maybe that's the energy. Maybe this is the Hamiltonian. This is the wave function. That's the energy, and there's the wave function. Now, how can these be operators and how these can be wave functions? I'll show in a minute. Let me do another example. Let me show you that there are 2 eigenfunctions of this operator. Here's the operator. Here's the other eigenfunction. And I'll just go ahead and tell you that the eigenfunction is 2, and here is the wave function again. So there you go. Operator, thing, number, thing. Just like quantum mechanics, except really a lot easier, right? And you know what this could be? This could be like the ground state. It has a low energy. Here's the excited state. It has a high energy. Minus 2 eV, ground state. 1, 0 is the ground state. The excited state is 0, 1. It's like the exact opposite. It kind of makes sense, right? And it has a higher energy of plus 2. Remember, low numbers are good, high numbers are bad when it comes to energy. Okay, so again, you can see a little bit about how this works. How matrices work, right? Real simple. What are we going to apply it to? We're going to apply this to, let's think about an H atom. What we're going to apply this to is an H2 atom. H2 molecule. We're going to start forming molecules. Again, I'm talking about this next Wednesday, but I just wanted to make use of this time, and I will be brief. So let's think about H atoms. Let's review what we know. Now, H atoms have 1 electron, and it has a Hamiltonian that goes across the board a couple of times. Remember how much fun that was. And we looked in a 17th century math textbook, and we saw that there are 1s orbitals, which is the ground state, but there are other states. There's an infinite number of states. There's a 2s state, which we can occupy that. We can make the electron go into a 2s state. And then there's 2p states. There's 3 of them, a px, and a py, and a pz. If the electron is in the 1s, I can send it to a 2p by absorption of light. So yeah, there you go. I mean, we've covered all this stuff. Okay, the wave functions, let's do well, it doesn't matter which one. The wave functions are like e to the minus r over a naught. That would be for 1s. It'd be like minus r over 2 a naught for an n equals 2. Whatever. It's e to the minus r a naught. Then we've got some angle bits. So this could be like cosine theta. That would be for a pz. And then we would have spin, like alpha or beta. But for a hydrogen atom, it doesn't do anything. Remember that we only needed to worry about spin when we had multiple electrons, because we had to do that Pauli principle. We had to make sure that we couldn't have 2 spin-up electrons in a 1s state, because that's not allowed. 2 electrons in the same state. Okay, so again though, I'm perfectly capable of describing the electron in a hydrogen atom as e to the minus r, maybe if it's in a pz or a px, blah, blah, blah. Alpha, beta, not that that matters. It only matters, I mean, it's still there, but it only really matters if we're worried about H, like H minus, right? We covered all of those. Okay, now here's the thing. When it comes to an H2 molecule, what I would like, or multi-electron states, we run into a big problem. And maybe I'm flashing that Hamiltonian above my head. I got to remember to do that now. When you have more than one electron, because you have like H minus, or a carbon atom, or an oxygen atom, and all those things have more than one electron, you have a molecule which has more than one electron. You've got that Coulomb term with the electrons, with the R1 minus R2 in it, right? You have the electrons repelling each other. Now remember, I told you that means there's no separability. That means that there's no solving it. We cannot solve the Schrödinger equation for anything with more than one electron. It is impossible. So what we do is we make an approximation. What we do is, let's do an example that we know, right, so that you don't forget. So let's do an H minus. So this is a 2-electron hydrogen atom. Right, hydrogen atom like we've known it, except I'm going to add an electron. And normally the ground state has 1 electron in the 1s, but I've added 1 to the 2s. And it looks like I've made it a singlet state. Go me, whatever. That's what I just decided to do. Now, again, we cannot solve the Schrödinger equation the same way that we did when we did all this. You know, looking through a 17th century math textbook. There's no textbook for this one. What did we do? What we did was we said that the wave function is going to be like the 1 electron wave functions that we already know, and we'll put the first electron in that one, and we'll put the second electron in the 2s. Now remember that this 1s and 2s states, which are like this, come from the hydrogen atom with 1 electron. This thing has 2 electrons. This is not necessarily correct. In fact, it isn't. It's an approximation. So we're going to use the wave functions for orbitals of something with 1 electron for something that has 2 electrons. It is an approximation, but it's the only thing that we can do. It's the only known solution. Now, again, recall that you have to make the electrons indistinguishable, so you have to do this weird permutation of 1 and 2 and 2 and 1. And then you've got to do the spin part. Okay, this is a singlet, so the anti-symmetry has to be here, and we do that by, again, permuting which orbital has electron 1 and which one has electron 2. It's weird, but that's how we do it. And I need 2 brackets or it's not right. There we go. Okay, again, this is the wave function for the H minus singlet state with an electron in the 1s state and the other electron in the 2s state. And again, we've covered that. I just want to point out again that using these orbitals from the 1 electron Hamiltonian is an approximation. Okay, now here's what I want to get to next. So we know how to handle atoms. Right, and you do calculations of shielding, which you're doing on your homework. I think homework 10. Sorry, you'll see. But now, what about molecules? Now, we're going to make the same approximations of molecules. We're going to assume that the atoms have hydrogen-like orbitals. In fact, what I'll do an H2 molecule, and that will be, the easiest to deal with. Okay. Here's the nucleus, and here's an electron, and let's put it in a 1s state. So 1s form. Right. Now, here's where, again, we know how to deal with this, but now what I'm doing is I'm adding another hydrogen atom, and again, I'm not going to do anything weird. I'm going to have its electron also in the ground 1s state. Okay, now when I put these two together and they get close, you know what's going to happen. The electrons are going to kind of diffuse together, right? And that's a bonding orbital. Now remember what that means is that electron density crowds between the nuclei. Plus, minus, plus. That's electrostatic glue. That's a chemical bond. That's how this works. So what I need to do is be able to write the wave function of the molecule as a combination of the wave functions of a 1s for atom 1 and the 1s state of atom 2. How do I do that? Let me point out that there's another complication. Bonding, well, what about this one? You know that there's also antibonding, right? So remember, different phases, so let's say plus, minus, remember that stuff from your textbooks? Remember how it would color one orbital and the other one would be blank? So this is antibonding. And what this means is that there's a lack of electron density between the nuclei. So you've got plus, plus, and it doesn't like that. So that's repulsive. That's not a bond. Okay. Now, what we're going to do is, again, very important, assume that the 1s electron on the first hydrogen is just like this, and that the 1s electron on the second hydrogen is just like this. So we have this part done. It's not quite right, but what else can we do? Okay, so then how do I get to this part now? How do I get to this bonding and antibonding? Remember what we were, the matrices. That's how we're going to do it. We're going to do quantum mechanics. We're going to completely change the way we do quantum mechanics, and we're going to turn to matrices. Okay, now how does that work? So we're going to do the Hamiltonian matrix. And let me just show you. Now, this is a bit of an approximation. I want to make this as easy as possible to understand, but I'm going to simplify it slightly. And that means the answers aren't going to be 100% correct, but you're going to get the gist. And that's more important than anything. So I'll say it's approximately like this. What you do is we're going to have a 2 by 2 matrix, 4 elements, 2 by 2. The first, let's do the diagonal ones. It'll be easy to understand. Here we've got the integral of the 1s electron. Here's the Hamiltonian, just like that multi-electron Hamiltonian. I guess I'm showing that again, I'll remember to do that. This is the multi-electron Hamiltonian. And here is, again, the 1s state for the first atom. Okay. Now, let's do the other diagonal. And that will be for the second atom of hydrogen. So that's why I put a 2 there. And again, it's in the 1s state. So, this would just be the energy of a hydrogen 1s state, which you did on a homework, right? And this is the same. Just because it's another hydrogen atom doesn't mean that its energy isn't still, that thing you did on your homework, number 7. Right, number 7, I think, on homework 6. So you know the energies of a hydrogen 1s state. The cross terms are where it gets interesting. And so, now I may be forgetting, I may be getting the permutation wrong, but I think you do 1 on the left and 2 on the right. And I may have gotten that switched, but I'm going to stick with it. Oh, this bracket isn't right. That bothers me. There we go. Now it's right. Okay, that means that 2 is on the right and 1 is on the left. Okay, so there you go. Now, if you think about this, what it means is this is a hydrogen atom just by itself. This is the other hydrogen atom by itself. And the off diagonals represent their interaction. It kind of just makes sense, right? It's kind of intuitive, which is nice because that's rare. Okay, now what you do is, it's not hard. I mean, we know what these are. We know what the diagonals are. These off diagonals, you need a computer. You need a computer to figure those out. It can be done by hand, but it's pretty painful. So let's just say that, now we know what the 1s energy is. So we know what the diagonals are. And the off diagonals, you know what? I'm just going to call them minus epsilon. And that is the energy of the interaction. I say minus. I like to put a minus sign there because it's a good interaction. It's a bonding interaction, right? So it's downhill. So I like to put a minus there. Now, what we need to do is, let's say we're now going to use as our wave vector the first hydrogen atom and the second hydrogen atom, right? And now we need to get the energy of the bonding state, and the wave function has to come back. So it has to be like this. And as you can imagine, if you can kind of do it in your head, it don't work. Ta-da! Again, the Hamiltonian matrix is simple. You want to make the wave functions just the first atom and the second atom, but it don't work. That's not quantum mechanics. Remember, if you don't make the eigenvalue equation work, Hamiltonian wave function, energy wave function, if you don't make that work, you got nothing. Okay, so what do? Okay, it turns out, and this is also on your homework, I'm just showing you right now, that if H psi is equal to energy, if that's the case, then you can rearrange it like this. Right? A high school student could tell you that. And where H minus E looks like this. Now I got to be careful here. Let me make sure you know what this is. This will be the energy of the molecule. And guess what? We'll have two of them. One for the bonding, one for the anti-bonding. Now I'm not going to make there be two of them. Two energies are going to just come out. And I will know that one is bonding and one is anti-bonding. I'm actually telling you how it's going to come out. Now be careful. It is not the energy of the 1s state or the interaction, which is basically the bonding energy. It's not the same. So just, they're just, unfortunately, it's the same letter E, right? So just be careful that it's not the same thing. It'll be obvious in a minute. Okay, now what does this look like? H minus the eigenvalue. It looks like this. E1s minus, again, that's the molecular orbital energy, the molecule's energy. The diagonal terms are not affected. So you see that the eigenvalues just end up coming into the diagonals. That's where they show up. Okay, now we need to do wave function equals 0. Okay, fine and good, but here's this weird thing that kicks in. This is like one of the most fascinating things I know. It turns out that, now let's forget this. Let's forget the wave function. Let's forget it equal to 0. It turns out that the determinant of this deal, H minus the eigenvalues, has got to be 0. That has to be true for there to be a solution. Now, what does it mean for there to be a solution? Okay, hold on one second. All this matrix, this and that, think about the first time you ever saw any of this jazz. You saw it when in 8th grade. What did you see? A plus B is equal to 1. A minus B is equal to minus 1. What is A? What is B? Right? You saw that with matrices. But you know that the trivial answer, everything is 0, is on the table. But that's not what you're looking for. What this says is that the determinant of this thing is 0, and if that's not true, then everything is 0, which is not an answer. So again, when you're solving those system of equations, if there's a meaningful answer to it, then this has to be true. Okay, thank you, theorem. But now guess what? It turns out that we use this to solve for the energies. Now, in case you forgot, the determinant of a matrix, A, B, C, D, is A, D minus C, B. It's diagonal one minus diagonal of the other. Okay, so that's what the determinant is. Now, what happens is, let me see, where am I at? What happens when you do this is you find that the energies, I'm actually not going to do this, you're going to do it on your homework. I'm just going to go ahead and tell you what the answer is. See, that's why this was worth watching. So it turns out the energies E, when you do this determinant and you set it equal to 0, I'm going to walk you through on your homework to show that the energies are going to be this. There's going to be one that's downhill and there's one that's uphill. Guess what? That's the bonding energy. That's the energy of the molecule in the bonding configuration. That is the energy of the molecule in the anti-bonding configuration. Uphill, downhill. So there you go. That's how it works. Again, in terms of solving this, you see you're actually going to have the reason you get 2 is you're going to have a quadratic equation. Again, you're going to see that on homework. The homework you have now. You're actually doing this on the homework you have now. Okay, now when you have the eigenenergies, the eigenvalues, then you can figure out the states. The bonding state, so for the molecule, is going to be the sum, or, so that's the bonding. So the anti-bonding state is like this. It's just minus. Okay. So, yeah, so that's how you use matrices to do quantum mechanics. And again, I just wanted you to see something about that. And then I'm going to give you one more example. So, and I'm going to do the case of spin wave functions. So let me wipe out the board and I'll be right back. Okay, last example of how matrices are used in quantum mechanics. Again, this part is, I'm going to do some reviewing, so this might be useful to you. For the most part, in terms of the nitty-gritty details, I'm not going to bring those up again, because this is the extra hour. Now see, what I wanted to do about this was I wanted to go back and look at the spin wave functions for our H- atom, which, if you recall, well, here, let's put some possibilities down. How about up, up? Okay, and we'll forget 2 p's. Let's not worry. There's no 2 p's. It's going to be 1s, 1p. So that's our hydrogen atom with an extra electron. I'll have 1 electron in the 1s, and I'll have the other electron in the 2s. I think I messed that up earlier. Okay, so we can have this configuration. Both of them spin up. Now that would be a magnetic state. It's a triplet. You remember we talked about this. Now I could also do this. I could have this one up and that one down. That's another possible configuration. I could have also, I have the inverse, and then I could have them both down. Okay, so those are the 4 possibilities. Now hopefully you recall, which is why I'm doing this, it's a bit of a review, that for the H- atom, there's a singlet state, which is non-magnetic or dimagnetic. That's the professional word. Dimagnetic means non-magnetic. And then there's the triplet states, which are paramagnetic, which means they are magnetic. That's like a bar magnet type, refrigerator magnet type of magnetism, not NMR type magnetism. That's a different form of magnetism. Okay, now I can recognize up, up, down, down. Those are triplets. But now I've got 2 others. What the heck do I do with those? Now, I actually gave you the spin wave functions, so maybe you recall, but regardless, what I did last time was I simply told you what the spin with the singlet and the triplet wave functions are. I just told them to you and said accept it. Let me derive it, and to do that I'm going to use a matrix. Now before I do that, let me remind you that spin is a type of angular momentum, just like P, 2s, 2p, the 2s state has no angular momentum, the 2p, the electron's rotating, 3s, 3p, 3d, right? The d states are rotating even more, right? Now, you may recall that the Hamiltonian for when we were talking about rotation in 3 dimensions, and we live in 3 dimensions. That was a 3D rigid rotor. It was a bit of a bear, wasn't it? So recall that the Hamiltonian was, I never used this notation before, but I'm going to call it L. I'm going to say L squared over 2I. So this is the 3D rigid rotor, and I is still the moment of inertia. So it's momentum, it's an angular momentum squared over 2 moment of inertia. That's the energy of rotation in 3D. Now again, I'm just using a different letter, just to remind you of how this works. And recall that that was minus h bar squared over 2I, that was familiar. And then you remember all this stuff, 1 over sine. Remember how awful this looked? And here's our phi. And I haven't separated it, but that's not my point. Yeah, this is a bit overwhelming, isn't it? So hopefully you remember all this. And you remember that the wave functions, remember you just did a problem set with a whole bunch of these rotational wave functions when you did the spectroscopy problems. So there you go. Okay. Now this is for the angular momentum of the electron, like orbiting the nucleus like the moon orbits the Earth. But the moon also rotates on its own axis, which is a different type of angular momentum. Now remember that that spin, S, so let's talk about S. We don't need to worry about the 2I. That's not really important. Let's talk about the spin type of angular momentum. Remember, the electron is not actually rotating on its axis. It's as though it's rotating on its axis, but it's not really doing that. Okay. It turns out that we don't have a crazy bunch of sines and thetas for spin-type angular momentum. Remember, we don't know what this really is, so how could I have an equation for it? I don't. I don't know what it is. However, we do have an ability to write the spin-squared matrix in, I just said it. I can write the operator as the form of a matrix. I cannot do it this way, but I can do it as the form of a matrix. Now the way we do that is we think about electrons in magnetic fields. Remember how I kept saying that singlets are not magnetic and triplets are? So what we do is we use magnetism to figure out what the S-squared operator is. Even though we don't know what spin is, we know how it operates in a magnetic field. So we can construct the Hamiltonian in a magnetic field, and then we can just say, well, the magnetic field is 0. So it's a bit of a trick. It takes me about 3 weeks to show my grad students. I teach this in grad school. It takes about 3 weeks to show how to do it properly. It's a bit of a pain, but hopefully you get the gist. Mainly it's a matrix. Okay, so I'm going to construct the S-squared matrix. And as before, I'm going to have rows and columns. Here's my rows. And now I'm going to have columns that are the same. So up, up. And now I've got a matrix element right here. Now again, if you come to grad school, I'll show you how to derive the S-squared matrix. It turns out that the element here is 2, and all the others are 0. Okay, next row, next column is down, up. Down, up. Okay. This is 0. With itself, it's 1. Okay, it gets a little weird because 1 there and 0. Okay, the next one is, that's up, down, then it's down, up. 0, 1, 1, 0. And then the last one, if the last one on the row is down, down, and the last one on the column is down, down. It's symmetric. Right? And that ends up being 0, 0, 0, 2. Now again, you don't know what this matrix is unless you come to grad school, and it takes me a while to show you how to do it. Okay, now what you do is you do that whole trick of subtracting the eigenvalues. The determinant is 0, yada, yada, yada. Actually, I use a website, the same one that you're going to use on your homework. And you get this. You get eigenvalue. And then there's another thing you can do to get the state, which I'm actually not showing you how to do that. But hopefully that's not like the worst thing I could ever do to you. Okay. Now, if you go onto the Wolfram website that you're using for your homework, you could plug this into that too. And here's what you get. This is how I did this. You would get an eigenvalue of 0. Okay, so what is that? That's a singlet. That means it's not magnetic. S squared is 0 means that there's no spin. Spin is how electrons are magnetic. So therefore there's no magnetism. That state would be, it would be this. Up, down, minus, down, up. Now you may recall that's the singlet state. Now we then find 3 more eigenvalues. Sorry, an eigenvalue of 2. Eigenvalue of 2. One of them is this up, up. There's another one, and it's down, down. And then there's a third with an eigenvalue of 2. And these are magnetic because there's a net spin, and spin is magnetism. That's where it gets its magnetism. The last one is up, down, plus down, up. There you go. That's where they come from. Now remember at the time, again, I wanted to do a little reviewing. I told you that the triplets, you know, you can kind of, it's intuitive up, up, and down, down. And the magnetisms are like enforcing each other. That's why these are magnetic. One is up, the other's down. And this one, which I said I really can't explain, it's when the magnetism is in plane, right? So that's as much sense as I was able to describe at the time, but this is where it really comes from. So there you go. So I am ending early. I just wanted you to see a little bit about this. I wanted to review a little bit more about spin wave functions, angular momentum, hydrogen atom electronic structure. So I've done a little bit of that. Again, you will actually see the hydrogen atom on Wednesday, and then you're going to actually solve what I did for the hydrogen molecule on problem set 10, and you're also going to do an oxygen molecule on problem set 10. Here's the hint. I'll give you a hint if you watch this far. On Wednesdays, this coming Wednesday's lecture, I'm going to show you the molecular orbital diagram of oxygen. That's the answer to one of the questions on problem set 10. So that's your reward for watching this far, and I thank you all.